Okay, let's get into it. We are definitely navigating some pretty deep waters today, scientifically speaking.
Absolutely. We're talking large-scale climate intervention, stuff that sounds like science fiction, but, well, it's being seriously discussed.
Yeah, seriously. And today we're doing a deep dive into sources around stratospheric aerosol injection, or SAI. These are projects basically designed to, well, dim the sun artificially.
That's the goal, yeah. Reflecting sunlight back into space. We've got some proper scientific assessments here, looking at how aerosols actually work up there in the stratosphere.
But then, right alongside those, we have these really strong critiques. People calling these technologies, false climate solutions, or sometimes even worse.
A polarized field.
Totally. So our mission today is kind of twofold. First, understand the science, this idea of mimicking volcanoes. It's actually quite elegant in a terrifying way.
It is. The physics makes sense on paper.
But then right after that, we have to confront the ethics, the economics, the politics driving these huge projects.
And we kind of have to start with the elephant in the room, don't we? Or maybe the demon in the acronym.
Ha! Yeah, exactly. There's this one project name that just jumps out. It feels less like science and more like, I don't know, provocative marketing. Maybe
Yeah.
designed to distract.
It certainly grabs your attention. It's almost like self-sabotagingly provocative.
Right. So let's just put it out there. We are going to be looking closely at a project known, unbelievably, as S.A.T.A.N.
That's S.A.T.A.N, standing for Stratospheric Aerosol Transport and Nucleation.
Stratospheric aerosol transport and nucleation. Satan. I mean, one of our sources literally calls it demonic geoengineering.
Yeah,
That name alone just casts this huge shadow of suspicion over everything, doesn't it?
it really does.
It's so wildly provocative, you have to wonder, is this some kind of extreme transparency? Or is it, like, intentionally inflammatory? Maybe even trying to normalize something critics already think is some kind of conspiracy.
That's the crux of it, isn't it? The fact that something called Satan is even being discussed in, semi-academic or regulatory circles.
Mm-hmm.
For critics, that's a massive red flag.
Yeah.
It feeds into this idea that maybe there's a shocking lack of, let's say, public relations sense, or maybe more worryingly, a deliberate attempt to court controversy.
Or hide in plain sight, almost.
Okay, so let's peel back the layers on what actually happened with this Satan project, beyond the name.
Right, the specifics. Who was behind it? What did they do?
Okay, so it was led by an independent researcher, Andrew Lockley. He was previously linked with University College London, UCL, and he worked with a company called European Astrotech.
European Astrotech. Okay, and the actual test, when was this?
It was surprisingly recent, September 2022.
Right, and what did they physically launch?
They used a high-altitude weather balloon,
Yeah.
launched from Aylesbury, over in the UK.
Okay. And the payload, what was it carrying? Because the name suggests something pretty dramatic.
Well, this is where the scale gets almost anticlimactic compared to the name. The payload released just a few hundred grams of sulfur dioxide, so, into the stratosphere.
A few hundred grams, that's it.
That's it. I mean, it's negligible compared to even a small volcanic eruption, let alone the big ones we'll talk about.
So, okay, if it wasn't about actually cooling the planet because a few hundred grams won't do anything, what was the stated purpose?
Right. The stated goal was all about the logistics, the
Mm.
procedure. Lockley said they were testing a low-cost, controllable, and this is important, recoverable balloon system.
So testing the delivery drone, essentially.
Pretty much designed specifically for future geoengineering purposes. They weren't trying to change the climate then and there. They were testing the vehicle, the injection mechanism, trying to see if they could build a viable, scalable way to get aerosols up there.
But the name, it just overshadows everything. The critiques, the sources calling it demonic geoengineering, they're not really focused on the amount of SO euros, are they?
No, not at all. Interestingly, they often focus on the fact that Lockley actually tried to do things by the book, procedurally.
What do you mean?
Well, that's where the tension really lies. This experiment, despite the name, was notable because Lockley went through the process. He got official flight permits. He submitted a notice to airmen, to the aviation authorities.
So he was trying to be transparent, following safety rules.
That seems to have been the aim, yeah. The system apparently had instrument tracking, safety features too, designed to stop the balloons landing somewhere with, like, dangerous gases still inside.
Okay, see, that procedural correctness makes the sensational name feel even weirder, almost insidious.
Oh, so.
Like, it's an attempt to legitimize the technology by following rules, but using language that seems designed to confirm the worst fears of people who are already suspicious.
Yeah, it definitely plays into that narrative of shadowy actors doing controversial things, even if they are ticking the boxes.
It makes it hard to take the transparency claims at face value when the branding is so aggressive.
Exactly.
Right.
And you can see the contrast with other efforts, right?
Hmm.
Like that company makes sunsets.
Oh, yeah, they just went ahead and did it, didn't they? Tried to sell cooling credits.
They did. Completely tried to bypass the regulatory process,
Yeah.
and they got widely condemned for it. The Mexican government actually stepped in and banned solar geoengineering experiments after their launches.
So that shows how crucial that regulatory approval and transparency really is.
Mm.
Even if, in Lockley's case, the chosen acronym was less than subtle.
Understatement of the year.
But still, the choice of Satan, knowing the heat around SAI, knowing the opposition, it feels like either a calculated move to get attention, maybe divert it in a weird way, or just a staggering lack of awareness about the global risks and sensitivities.
Or maybe a belief that any publicity is good publicity when you're trying to push a fringe idea into the mainstream.
Perhaps. It certainly makes it incredibly difficult for anyone trying to have a rational public debate. How do you separate genuine science from what looks like a cynical push for a controversial agenda?
And that dual nature, this weird packaging, combined with an attempt at procedural correctness, that's really why the whole SAI debate is just so fiercely polarized.
Yeah.
It gives critics perfect ammunition to say, look, this whole field is fundamentally deceptive, regardless of how many grams of sulfur they release.
So the bottom line on Satan is
Hmm.
the actual physical test was tiny, a proof of concept.
Right.
But the concept they're trying to prove, the one they want to mimic, that's anything but small.
Well, that takes us into the realm of massive natural forces, the kind that actually can change the global climate.
Okay, so let's get into the core science here. Stratospheric aerosol injection, SAI. It falls under the umbrella of solar radiation management, or SRM.
Right.
And the basic idea is actually surprisingly simple. You inject reflective particles, usually something based on sulfur, way up into the stratosphere,
And those particles then scatter sunlight back into space before it warms the Earth.
cooling the planet. It sounds straightforward enough.
And the reason scientists are even considering this is because we've seen it happen naturally. They're trying to replicate the cooling effect observed after really big volcanic eruptions.
So this isn't just theory. We have real-world data showing this mechanism works.
We do. There's no guesswork about the basic principle. Large volcanic eruptions demonstrably cool the planet for a year or two afterwards.
And the big one, the eruption everyone points to as the benchmark, that's Mount Pinatubo in the Philippines, right? What happened there in 91?
Pinatubo is really the gold standard for studying this in modern times. It blasted an enormous amount of sulfur dioxide. Estimates range from about 17 to 20 teragrams.
Teragrams. How much is a teragram?
A teragram, Tenny, is a trillion grams, or a million tons.
Yeah.
So 17 to 20 million tons of cerosol.
Wow.
Okay, directly into the stratosphere. And that cerosol injection eventually created a total stratospheric aerosol load, the actual reflective particles, around 30 teragrams.
30 million tons of reflective haze.
Exactly. And just that one event basically dominated the stratospheric aerosol picture for the last quarter of the 20th century.
So compare that 30 million tons to the few hundred grams in the S.A.T.A.N test.
Yeah, the scales are just mind-bogglingly different. It's almost incomparable.
And Pinatubo wasn't the only one, right? There was El Chichon before that.
Right, El Chichon in Mexico, 1982. That injected maybe 70 grams of SO, so still massive, but less than half of Pinatubo.
Okay, so once all that SO gets shot up into the stratosphere, what happens chemically? How does it form this reflective layer?
The SO gas doesn't reflect sunlight very well itself.
Oh.
It needs to transform. It undergoes chemical reactions up there, driven by sunlight photooxidation, and eventually forms tiny droplets,
Droplets of what?
primarily aqueous solutions of sulfuric acid, HSO, and water. These tiny droplets are the actual stratospheric aerosol particles that scatter sunlight.
And how do they form? Do they need something to condense onto?
Mostly, they form through something called binary homogeneous nucleation, which is just a technical way of saying the sulfuric acid and water vapor molecules, under the right conditions, spontaneously clump together to form new particles.
Okay. And this happens particularly in rising air near a specific atmospheric zone.
Yes, a really critical region we need to talk about, the tropical tropopause layer, the TTL.
Right, the TTL. Break that down for us. What is it, and why is it so important for this process?
Okay, think of the TTL as this kind of transition zone, a gateway sitting above the tropics, roughly between the troposphere, the turbulent lower atmosphere where our weather happens, and the very stable, dry stratosphere above it.
The gateway to the stratosphere.
Exactly. It's crucial because Air rising vigorously in the tropics, like in big thunderstorms,
Sure.
can punch through the tropopause and carry gases from down here right up into this TTL region.
And from there into the stratosphere proper.
Right, and once gases like Okieros get into the stable stratosphere, they can stay there for a long time, years, even because there's no rain up there to wash them out quickly.
Okay, so the TTL is the efficient delivery route for these aerosol-forming gases.
Precisely. Especially for gases injected by tropical volcanoes like Pinatubo.
So once these sulfuric acid particles are formed and floating around up there, how long do they actually last? This seems critical. If we did start injecting deliberately, how long would the cooling effect persist if we stopped?
That question of lifetime and decay. That is probably one of the biggest, trickiest challenges in modeling SAI. It's not straightforward.
What does the data from Pinatubo tell us? How long did that aerosol cloud stick around?
Well, the volcanic aerosol signal from Pinatubo did eventually fade from the long-term measurements, but it took somewhere between, say, 4.5 and 7.5 years, depending on the latitude you were looking at.
4 to 7 years. Okay, that sounds maybe manageable, but you said it's complex.
It is, because the decay doesn't happen at a constant rate. It's not like a simple half-life. This is where the models get really complicated and, frankly, a bit scary. The decay is nonlinear. The models show that the E-folding timescale, that's basically the time it takes for the aerosol concentration to drop by about 63%, a standard measure.
Yeah.
That timescale gets longer as the particles get older and smaller.
Wait, so the effect lingers more effectively as time goes on, even as the total amount decreases? Why does that happen?
It's related to how the particles are removed. Larger particles fall out faster due to gravity, and they also coagulate, sticking together and falling faster. As the larger ones disappear, you're left with smaller particles that fall much more slowly and are removed less efficiently.
Okay, so what does that mean for the decay timescale? You mentioned Pinatubo.
Right after Pinatubo, when the concentration was highest and particles were larger, the E-folding timescale was maybe less than a year. Things were clearing relatively quickly.
But then?
But as the aerosol cloud aged and thinned out and the average particle size dropped, that timescale stretched out dramatically. Models suggest that between 1997 and 1999, years after the eruption, the E-folding time reached values of 40 years.
40 years. 40.
40 years, meaning the last remnants of that aerosol layer were decaying incredibly slowly.
Okay, that is profoundly different. 40 years. What are the implications of that for intentional SAI?
The implications are huge and, frankly, terrifying. It leads directly to this nightmare scenario called termination shock.
Termination shock. Explain that.
Okay, imagine humanity starts a large-scale SAI program. We're injecting aerosols constantly to keep the planet cool, offsetting maybe 1 or 2 degrees of greenhouse warming. The climate adapts to this new, artificially cooler state.
Right.
Now imagine something happens, a major war, an economic collapse, a catastrophic failure of the delivery systems, and we suddenly have to stop the injections. Abruptly.
Okay.
Because of that long decay tail, the cooling effect wouldn't just switch off instantly. But the underlying warming from all the greenhouse gases we kept emitting, that's still there. It's been masked, but it hasn't gone away.
So the mask comes off.
Exactly. And it could come off terrifyingly fast. Temperatures could rocket upwards, potentially several degrees Celsius within just a decade or maybe even a few years.
That would be catastrophic.
Unprecedented climate chaos. Imagine droughts, floods, heat waves, far worse and far faster than anything we're experiencing now. Crop failures on a global scale could be far, far worse than the gradual warming we were trying to prevent.
So this nonlinear long-tail decay makes stopping SAI potentially more dangerous than the warming itself.
It's a major, major risk, and it makes predicting the consequences of stopping incredibly difficult.
It fundamentally changes the nature of the commitment, doesn't it? It's not a temporary fix you can just turn off.
It looks much more like a potentially perpetual planetary scale intervention, a commitment you might not be able to safely end. It creates a kind of dependence.
An addiction to planetary manipulation. Wow. Okay.
Now, while these big tropical eruptions like Pinatubo dominate the picture when they happen maybe for 20 out of the last 30 years, the sources say there's also a constant background aerosol layer.
Right. The stratosphere isn't perfectly clean even without volcanoes. What maintains that background layer?
It's formed from sulfur-containing trace gases that make their way up from the troposphere from down here.
Okay, what are the main ones, besides the SO from smaller volcanoes or industry?
The primary non-volcanic source gas that contributes significantly is carbonyl sulfide, OCS.
OCS, why is that one particularly important?
Because, unlike SAT, OCS isn't very soluble in water. That means it doesn't get washed out by rain easily in the lower atmosphere.
Ah, so it survives the journey up to the TTL and stratosphere more easily.
Exactly. It's more readily transported upwards intact. Some chemistry models estimate that maybe up to 30% of the background stratospheric sulfuric acid actually originates from OCS oxidation, with the rest coming from SO sources.
Okay, so OCS is a key background player, and the sources also mentioned space dust.
Yeah, kind of amazing, isn't it? Meteoritic material continuously raining down on Earth. The estimated flux is something like 44 tons per day.
44 tons a day.
Yeah. And during times when there haven't been recent big eruptions, volcanically quiescent periods, this cosmic dust might actually make up over 10% of the total mass of stratospheric aerosols.
So it acts as tiny solid cores or mixes in with the acid droplets.
It seems to act as non-aqueous components within the particles, yes.
Mhm.
Adds another layer of complexity.
And we add our own space junk too, right? Rocket launches.
We do. Solid-fueled rocket motors, in particular release particles, mostly aluminum oxide, aluro. One estimate put the total stratospheric emission of alumina from rockets at around 1,800 tons per year, based on typical launch schedules back then.
So the stratosphere is this complex soup. Volcanic remnants lingering for decades, background OCS, cosmic dust, rocket exhaust.
It's a dynamic system we're still trying to fully understand.
And into this complex, naturally balanced system, projects like S.A.I. and even the tiny S.A.T.A.N test propose deliberately intervening, seizing control almost.
That framing, seizing control, is precisely why it generates such profound ethical opposition. Which brings us squarely into the critiques. Okay, so stepping back from the aerosol science itself, we get into the policy and ethics. And here, geoengineering faces a wall of criticism. Many groups see it as posing, and this phrase comes up again and again, unacceptable and potentially irreversible risks.
And this isn't just fringe concern, right? This opposition has teeth at the international level.
It does. Global governance bodies have been wary. The UN Convention on Biological Diversity, for instance, has called for what's essentially a moratorium on these kinds of climate-related geoengineering practices, citing the precautionary principle.
A moratorium, so a halt to deployment.
Pretty much, yeah. Reflecting global nervousness about unintended consequences for ecosystems and biodiversity, and specifically for ocean-based techniques, the London Convention and Protocol, which govern ocean dumping, have put in place rules that act as de facto bans on most marine geoengineering.
Okay, so there's significant official resistance. But why? If the climate crisis is so urgent, why reject potential tools, even risky ones? What's the fundamental objection from groups like, say, Friends of the Earth in the source material?
The core objection is structural, really. Critics argue that geoengineering, particularly SRM like S.A.I., functions mainly as a dangerous distraction.
A distraction from what?
From the thing we know we need to do. Make urgent, deep, drastic cuts in greenhouse gas emissions. Reduce our reliance on fossil fuels.
So the argument is it's a techno fix that lets polluters off the hook.
That's exactly the argument. It's seen as offering a technological band-aid, a way to potentially manage the symptoms of climate change without addressing the root cause. Critics argue it allows politicians and corporations to avoid the difficult choices needed to actually transition away from a high-emissions economy to maintain a failed status quo.
But proponents would argue we need to buy time because emission cuts aren't happening fast enough. Where does the critique focus its counterattack?
It really focuses on the potential for moral hazard and the economic entanglement. The fear is that the mere possibility of geoengineering weakens the political will for mitigation. Why make tough carbon cuts now if there's a magic bullet later?
Right.
And it diverts resources, research funding, political attention away from scaling up renewables, efficiency, and actual emission cuts. To see how this plays out, we can look at another category often lumped in as false solutions. Carbon dioxide removal, or CDR.
CDR, pulling carbon out of the atmosphere rather than just blocking sunlight.
Exactly. Specifically, let's look at carbon capture, utilization, and storage, CCUS.
CCUS. That involves capturing co-rows from power plants or industrial sites, right? Or even directly from the air.
Yes, either from flue gas, that's post-combustion capture, or direct air capture, DCCS, pulling it from ambient air.
Okay, sounds good in principle. What's the main critique there?
The big one is energy and cost. The actual process is using chemical solvents to absorb co-rows, compressing the gas, pumping it somewhere, sometimes running huge fans for DACCS. They're incredibly energy intensive. And critics argue that the massive amount of energy needed to capture 1 ton of carbon often requires burning more fossil fuels, which releases more carbon. So the net benefit can be small, or even negative, depending on the energy source.
So it's potentially inefficient and very expensive.
Hugely expensive, yes. Which means it often relies on subsidies, and critics argue that money could be better spent on proven solutions like wind and solar.
And beyond efficiency, there are physical risks too, right? Handling all that captured CO2 fuel.
Absolutely. This isn't harmless stuff.
Yeah.
Once you capture the CO, to transport it or store it underground, you have to compress it into a very dense, semi-liquid state called supercritical co-euro.
Okay.
This stuff is highly concentrated Q-euro. It's invisible, odorless, heavier than air, and it's an asphyxiant. In high concentrations, it displaces oxygen.
So if it leaks.
If a pipeline carrying this dense Q-euro ruptures, it can release a heavy, ground-hugging cloud that can suffocate people and animals very quickly. It's also toxic at high concentrations, affecting body chemistry.
And this isn't just a theoretical worry. The sources mention a real-world incident in Mississippi in 2020. That sounded pretty bad.
It was horrific. A pipeline carrying co-euro operated by a company called Denbury, Inc. ruptured near the town of S.A.T.A.N, Mississippi.
What happened to the residents?
The gas escaped, apparently freezing the ground around the rupture, and formed this invisible cloud that rolled into the community. People suddenly found themselves nauseous, gasping for air, unable to breathe properly. Cars stopped working because the engines were starved of oxygen. First responders were overcome.
Just chaos. And were there lasting effects?
That's what's really concerning. Months later, residents were still reporting serious health problems. Persistent fatigue, cognitive issues often described as mental fogginess, ongoing lung problems, stomach disorders.
Wow.
There was a real wake-up call about the dangers of building out potentially thousands of miles of high-pressure co-euro pipelines, often near communities, which is what scaling up CCUS would require. Any failure could be catastrophic.
And the company involved, Denbury, Inc. They weren't just capturing and storing this Q-euro purely for climate reasons, were they? This connects back to that economic critique.
Exactly. This is where we get into the really problematic linkage that fuels so much of the criticism. The single biggest reason critics label CCUS a false solution is its deep, almost inseparable connection to the fossil fuel industry through something called enhanced oil recovery, EOR.
EOR, right. Explain how that works and why it's so controversial.
Okay, so enhanced oil recovery is a technique used to get more oil out of old, depleted oil fields. What they do is take captured scuro, compress it like we discussed, and inject it underground into these oil reservoirs.
Why inject CRO?
The curo acts like a solvent down there. It mixes with the remaining oil, making it less viscous, less sticky, and it also helps maintain pressure in the reservoir. This pushes residual oil toward the production wells.
So it basically squeezes out the last drops of oil that you couldn't otherwise reach.
Precisely. It allows companies to maximize extraction from existing fields and access oil that was previously uneconomical to recover.
And the Q-euro often stays underground then. That's the storage part.
Some of it stays underground, yes, but the primary economic driver for many CCUS projects, especially in the U.S., hasn't been climate mitigation. It's been selling that captured Q-euro to oil companies for EOR.
So taxpayer money or subsidies going into carbon capture are effectively subsidizing more oil production.
That's the core critique. Public funds intended to fight climate change are being used in a process that directly leads to the extraction and eventual burning of more fossil fuels, releasing more Q-euros. It's seen as a completely perverse incentive.
Yeah, it locks in fossil fuel infrastructure rather than replacing it. And EOR itself isn't without risks either, beyond the pipeline issues.
No, the injection process itself can be hazardous. The sources mention another incident, also involving Denbury, at their Tinsley EOR project back in 2011.
What happened there?
They had a co-euro blowout. The injected gas basically exploded back out of the ground under high pressure. It injured a worker and tragically killed local wildlife around the site.
So these incidents really highlight that EOR isn't just enabling more fossil fuels, it's actively introducing new environmental and safety risks associated with handling high-pressure Q-euro in the field.
Correct. It's part of the fossil fuel system, not a solution separate from it.
Okay, let's shift gears slightly to direct air capture, DAC, pulling Q-euros right out of the ambient air, anywhere. That sounds like it avoids the direct link to power plants.
It does avoid the point source link, yes. DAI uses chemical processes, often involving large fans pulling air over specialized filters or liquid solvents that absorb the Q-euro.
Sounds appealing. What's the catch?
Scale. The sheer scale needed is just astronomical, and the current reality is tiny.
How tiny?
Okay, so climate models suggest we might need to remove billions of tons of Kyoros from the atmosphere annually by mid-century to meet net zero goals. Billions.
And current de-ice facilities.
All the DD plants operating worldwide today, combined, capture less than 10,000 tons of Carioro per year.
10,000 versus billions.
Yeah, it's a difference of, what, 5 or 6 orders of magnitude? The gap is enormous.
What would closing that gap even look like physically?
It would mean building an entirely new global industry from scratch, on a scale comparable to, say, the entire current cement or steel industry. Huge facilities, massive energy demands. The land use, the resource requirements would be immense.
And the energy needed to run all those fans and chemical processes, where does that come from?
That's the other major challenge. Ideally, it would be clean energy, but the sheer amount needed is vast. If it comes from fossil fuels, you run into the same problem as CCUS. You might emit nearly as much Carioro generating the power as you capture.
And yet, governments are investing heavily in this. You mentioned the U.S.
Yeah, the Biden administration committed $1.2 billion for 2 large DAC hubs, one in Texas, one in Louisiana.
And is that funding controversial?
Yes, highly. Because at least one of the projects, run by Occidental Petroleum's subsidiary 1.5, formerly Oxy Low Carbon Ventures, who also proposed the Stratos project, has explicitly stated they intend to use the captured SATARO for, you guessed it,
Enhanced oil recovery.
enhanced oil recovery. So again, critics see it as public climate funds being channeled via DAC directly into prolonging the life of the fossil fuel industry.
It seems like a recurring theme. Okay, let's head out to sea. Marine geoengineering. What's happening there? The outline mentions ocean alkalinity enhancement, OAE.
Right. OAE is about trying to boost the ocean's natural ability to absorb Cariuros from the atmosphere. The ocean is already a huge carbon sink, but it's becoming more acidic as it absorbs Cariuro.
So how does OAE work?
The idea is to add alkaline substances to seawater, things like magnesium hydroxide or more commonly proposed finely ground silicate minerals like olivine.
Adding rocks to the ocean, how does that help?
When these alkaline minerals dissolve, they react with Cariuros in the water and effectively lock it up in other carbonate and bicarbonate ions. This process lowers the acidity locally and, crucially, allows the surface water to absorb more Cariuro from the air to restore equilibrium.
Okay, so it enhances the ocean's carbon uptake and fights acidification. Sounds potentially beneficial. Again, what's the catch?
Again, scale and the source material. If you use olivine, which is abundant, the chemistry works out roughly like this. You need to mine, grind up, and distribute about 1 ton of olivine for every 1 ton of Cariuro you want to remove.
1 to 1, that's a lot of rock.
It's a staggering amount of rock. To make a meaningful dent in global emissions using OAE with olivine, the sheer scale of mining required would be comparable to the entire current global production of things like coal or maybe limestone for cement. We're talking about creating a mining industry potentially larger than anything that exists today.
So we solve a climate problem by creating potentially the world's biggest mining and logistics operation, with all the environmental impacts that entails: habitat destruction, dust, energy use.
Exactly. You're trading one massive industrial problem for another. And there's another significant risk with olivine specifically.
What's that?
Olivine deposits often contain naturally occurring heavy metals, especially things like nickel and chromium, which are toxic.
So grinding up billions of tons of this stuff and dumping it in the ocean.
Could release significant amounts of these toxic metals into marine ecosystems. We don't fully understand the long-term impacts, but the potential for harm to plankton, shellfish, fish, and the entire marine food web is a major concern. It could affect organisms at the base and accumulate upwards.
Right. And there was one other marine idea mentioned: growing seaweed.
Yeah, macroalgae cultivation. The idea is to farm massive quantities of seaweed, like kelp or perhaps sargassum, which absorb Cariuros as they grow. Then you deliberately sink this biomass into the deep ocean, hoping the carbon stays sequestered down there for centuries.
Growing and sinking seaweed. What are the risks there?
Well, doing this on a climate-relevant scale would mean vast ocean farms, which could disrupt marine ecosystems and navigation. There are concerns about changing nutrient cycles in the ocean.
And the seaweed itself.
Seaweed, especially species like sargassum, can also absorb things from the water column besides Cariuros, including heavy metals like arsenic. So sinking massive quantities of it could potentially transport significant amounts of toxins to the deep sea floor, with unknown long-term consequences for deep sea ecosystems.
So it seems like across the board, from the provocative S.A.T.A.N project trying to mimic volcanoes to CCUS linked with oil recovery to DAC's energy thirst to OAE's massive mining needs to sinking seaweed, these large-scale geoengineering ideas run into really fundamental problems.
They really do. High energy costs, serious safety and toxicity risks like those Cuyero pipeline ruptures, ecological disruption, and very often this troubling economic linkage that seems to perpetuate the fossil fuel system rather than replace it.
Okay, so we've covered a lot of ground. We went from the micro level science of how tiny aerosol particles form and behave in the stratosphere.
A layer naturally supplied by things like carbonyl sulfide, OCS, and even space dust, and then occasionally reset by huge volcanic injections like Pinatubo, whose effects linger for decades.
Right. And we contrasted that natural system with these audacious, deliberate human attempts to intervene and control it, epitomized by that incredibly provocative, almost suspiciously named S.A.T.A.N project.
And then we looked at the broader landscape of climate intervention, CCUS, DDC, EOR, OAE, seaweed sinking, and saw this pattern emerge.
Yeah, this pattern of really significant downsides, massive energy requirements, serious physical risks like leaks and toxicity, ecological disruption, and this almost constant problematic connection back to extending the life of the fossil fuel economy, especially through enhanced oil recovery.
And specifically with SAI, we encountered that deeply worrying prospect of termination shock, the idea that starting it might be creating a commitment we can't safely stop, potentially locking us into perpetual planetary manipulation.
It really reframes it from a solution to a potential global addiction.
Now, to wrap up, let's circle back to the basic science of stratospheric aerosols for a final provocative thought for you, connecting these deliberate geoengineering schemes back to, well, just regular global pollution.
Okay.
Remember we talked about the importance of the tropical tropopause layer, the TTL.
Yeah, the atmospheric superhighway into the stratosphere, especially over the tropics.
Exactly. Well, some of the scientific sources looked at how changing patterns of normal industrial pollution, specifically sulfur dioxide, sulfur aero, might affect that stratospheric aerosol layer.
Not deliberate injection, just everyday emissions.
Right. What they found is that while regulations have been quite successful in reducing sulfur pollution in places like North America and Europe,
Good news, right.
yes, but emissions have been increasing significantly in other parts of the world, particularly in rapidly developing countries located in or near the tropics. Think parts of Asia, India, China, the Middle East.
Okay, and why does the tropical location of those increasing emissions matter so much?
Because of that transport mechanism we discussed. The strong atmospheric convection, think big thunderstorms, monsoons, it's common in the tropics, acts like a giant elevator,
Pumping that industrial SO straight up.
efficiently pumping it right up towards the TTL. And from there, as we know, it can easily enter the stratosphere, form sulfate aerosols, and linger for years, reflecting sunlight, just like volcanic ACE.
But wait, are you saying that regular industrial pollution from certain regions might already be inadvertently geoengineering the stratosphere?
That's the provocative question the science points towards. As humanity grapples with the climate crisis, what's actually going to have a bigger impact on the stratospheric aerosol budget in the coming decades? Will it be these deliberate, highly controversial, internationally debated SAI schemes, like the ones S.A.T.A.N was testing the delivery for? Or will it be the unintended consequence of shifting patterns of global industrial development? Billions of tons of anthropogenic SAO emitted in tropical regions, naturally lifted by atmospheric dynamics into the perfect position to create a reflective haze, essentially performing SAI entirely by accident, with no oversight, no international agreement, just as a side effect of economic activity.
Wow. So the scientific model suggests this accidental, pollution-driven geoengineering might already be happening and growing.
The potential is there, and the sensitivity of the stratosphere to these tropical emissions seems significant. It raises this ultimate irony. Maybe the biggest human influence on the stratosphere won't be a grand, deliberate plan like SAI, but just a messy, uneven, unintended consequence of how and where we industrialize.
A planetary manipulation happening by default, not design. That is definitely something to think about.
It certainly is.
Okay, that's all we have time for on this deep dive. We hope this left you feeling, well, thoroughly informed and maybe, yeah, just a little unsettled.
Until next time.